Welcome to Variational Principle and Lagrange's equations. Today we are going to discuss extensions of Hamilton's principle to systems with constraints. Until this point, the constraints of equation 137 have been dealt with by choosing coordinate systems such that they become a trivial set of equations. Hamilton's principle is applicable to holonomic systems and certain types of non-holonomic systems. This is a very subtle discussion, and mainly we are going to be talking about when we make reference to non-holonomic systems, we are actually going to talk about holonomic systems where the constraints are not given in integrated form. Deriving Lagrange's equations, holonomy is invoked only in the last step when we assume all the delta qi variations are to be independent. It is critical that these displacements are compatible with the equations of constraint. What we mean by this is that when we vary the path of motion in Hamilton's principle, the equations of constraint do not change with the varied path, and they remain the same for all paths regardless of the variations that are used to generate them. For a system having n variables and m equations of constraint, which we will label with f and x alpha, the extra virtual displacements are eliminated through the method of Lagrange undetermined multipliers. So we are looking at a more general form of Hamilton's principle, where to the initial Lagrangian of an unconstrained system, we append the sum of coefficients given by the equations of constraint multiplied with undetermined quantities at this point, which are the Lagrange multipliers. And we will see that generally they have the significance of forces of constraint acting on the system. Now, if we allow the q coordinates and the Lagrange multipliers to vary independently, we obtain a set of n plus m equations with the m variations of the lambdas giving the constraint equations. In delta q variations, we obtain the following. This is the variation of the action integral, calculated as in the previous sections. And the result is quite straightforward. Is a sum over I of integrated variations for each generalized coordinate between times t1 and t2, and the coefficient multiplying the variation has three terms. The first two are the usual ones, which we have just obtained previously, and the third one is simply the partial derivative of f with respect to the specific generalized coordinate entering the sum. The multipliers lambda are chosen such that m equations are satisfied for arbitrary variations, and the remaining n minus m equations have independent variations. That is, for the first m equations, we obtain the stationarity condition in the form of the vanishing of the coefficient given here. And this is true for the first m equation due to our choice for lambda. But the same follows for the rest of the equations from the index m plus 1 up to n, which in that case is true given the independent nature of the variations delta q. So in conclusion, the system is solved at the expense of introducing m unknown functions, which are the undetermined multipliers. Another way in which to write the previous result is to keep the left-hand side in the form of the standard Lagrange equation that we are familiar with, and move the sum involving the undetermined multipliers and the equations of constraint on the right hand side and identify this with q index k for k running from 1 to n, so for each equation, where these q's are simply the generalized forces needed to produce the individual constraints. But notice that only their magnitudes can be determined given the arbitrary plus sign in equation 222. So the plus sign is introduced here in the action principle, and it follows here either way. It doesn't matter how you choose the signs in this equation, but obviously if you move this to the right hand side, you end up with a plus sign, which is arbitrary in nature because we chose the plus here where it could simply have been a minus. So we can only determine the magnitudes of the generalized forces, but their direction can be found only by understanding the physics of the given problem. As a simple example, you can consider a smooth solid hemisphere of radius a placed with the flat side down and fastened to the ground within a constant gravitational field g. A small mass is placed at the top of the hemisphere with an infinitesimal displacement such that it can slide down without friction. In this case, the kinetic energy has the expression that we are very familiar with, written either in Cartesian or polar coordinates. The potential energy is chosen such that it is maximum at the top of the hemisphere and it goes to zero when the particle reaches the ground. And to these two functions, we also append the equation of constraint, which simply asks that the radius vector of the particle needs to be equal in magnitude with a, which is the radius of the hemisphere. And putting all these three things together, we obtain a Lagrangian, which is made up of the usual terms, t minus v, to which we add the undetermined multiplier lambda, which multiplies the equation of constraint. And then we construct Lagrange's equations the usual way. For the radial equation, we obtain the result here, labeled with an index 1, which, as you can see, it simply states that it states the undetermined multiplier as a function of theta and the square of the angular velocity. And you see that in writing this, so we have derived the equation, and then we have also applied the constraint. So r must be equal with a, which means, for example, that the acceleration vanishes since the radius vector needs to be constant. And that's how we end up with the result here. So we write it as an unconstrained equation, if you will, and then after writing it fully, we apply the actual constraint after derivation, and we end up with the result here. And similarly, we can write the Lagrange equation for the theta coordinate, and in this case, no constraints are involved, and we obtain something which, up to the sign here, looks like the usual pendulum equation. And now the trick is the following. So notice that we have obtained lambda as a function of theta and the square of the angular velocity, and we happen to know the angular acceleration as a function of theta. So the trick is that if we take the time derivative of the square of the angular velocity, the result is clearly the one here. This is evident, and then we can write the angular acceleration according to the result here, which leads to the next step in our equality, and then we simply integrate this formally so that the result is the one given here. This structure is just the time derivative of cosine of theta up to a sine. So now we can simply integrate these two sides, and we get the square of the angular velocity up to a constant c, which is determined from the initial condition, namely that at the initial moment at t equals 0, the angular velocity needs to be 0, so the particle is at rest. This allows us to determine the integration constant, and as such we obtain the square of the angular velocity as a function of theta. And now if we plug this in equation 1, we obtain lambda as a function of theta alone. And as said, this the physical significance here is that of the force of constraint acting on the particle. So it is the force exerted by the hemisphere on the particle, and which keeps the particle from falling straight down to the ground under the influence of gravity. And if, for example, we were to impose the condition that we want this multiplier to vanish, then for lambda equals 0, the solution of this equation is given by theta being the arc having the cosine of 2 over 3. So, in other words, the particle falls off the hemisphere at an angle of roughly 48 degrees. So this is the angle at which the reaction force exerted by the hemisphere on the particle vanishes, and this corresponds to a height of roughly 2/3 of the hemisphere's radius. So you see, this is a very nice result which allows us to predict exactly where the particle is going to come off the hemisphere. And a very similar problem is solved identically if instead of a hemisphere, we assume that we have a vertical hoop of radius a at the top of which the particle is placed, and everything follows identically with the procedure here. Variational principles are generally not applicable to non-holonomic constraints, and a very detailed discussion on this topic is given in an article found in the American Journal of Physics, published in the year 2005, and written by Martin Raymond Flannery, which covers many subtle points on this issue, and I just make use of its main conclusions in this presentation. And one of them is that an exception is sometimes an exception to the previous statement is sometimes presented by so-called semiholonomic systems, having general constraints of the functional form given by f depending on generalized coordinates, generalized velocities, and being in an arbitrary number, let's say m equations. And specifically, they are of the restricted form here. So they are functions which are linear in the generalized velocities, and in principle the coefficients found in these expressions can be functions of the generalized coordinates and time. I specifically say in principle because ultimately the main point is that the method works provided that the differential expressions f alpha have vanishing variations when varying the system path through configuration space in delta qi's, so when performing variations in the generalized coordinate. If this is the case, so if the differential expressions for f, the equations of constraint, so to say, do not vary along with the variation of the system path, then they can be treated through the generalized principle written here. So the variational condition applied to an action integral, which once again contains the unconstrained Lagrangian L and a sum over the equations of constraint uh, multiplied by these new factors, which we call mu, and which are specifically functions of time. In the third edition of Goldstein's treatise, the the corresponding Lagrange equations were given in the form presented here, and it is very easy to derive this on general grounds. Um, but the main problem is that the result here is generally wrong. So it will generally, if you apply it without checking that the the equations of constraint indeed have vanishing variations when varying the system path, which is equivalent to saying that if you don't check that the equations of constraint are exact differential forms, this result will lead to the wrong equations of motion. And it turns out that in order to obtain the correct equations of motion, you need to restrict this result quite severely. And specifically, this thing needs to vanish. And from the first term, the only thing which survives from this derivative is the term involving the time derivative of mu. So we have the usual left-hand side, which is the known Lagrange equation for the unconstrained system, being equal to a generalized force Q of index k, which is given by this expression. So minus the sum of the partial derivatives of f with respect to generalized velocities multiplied with the time derivative of mu. And it is this in this situation this multiplier will play a very similar role to the lambda multiplier from the previous discussion, and can be interpreted as being related to the force of constraint acting on the system. So these delta mu variations supply the equations of constraint 225, which were the ones given here. And thus we have obtained an equivalent holonomic system in n plus m unknowns and featuring generalized forces Q of index k. And as an example, we can consider the following generic Lagrangian, which is given by a standard kinetic energy written in Cartesian coordinates minus some potential function depending on the coordinates x, y, and z. And we are going to subject it to the constraint presented here. Now, in the last edition of Goldstein's book, this expression is a bit different, and I think it is wrong, because first of all, it features a square here, which will not really make sense, because then dimensionally you'll have a different dimension in this term as opposed to this term. Uh, we you cannot really compare it with the term here because you don't know what the dimension of the constant k is, but it is clear that these two are different. So either you have a square in both of them, or you don't have a square anywhere. So I chose just to omit a square. And also another problem is that in the book this the time derivative here is absent, so that the third term is simply k multiplying the coordinate set. And if this is the case, I'm not really sure that this is a good example, because you can check immediately that if you take the variation of this, if you take the variation of an equation of the equation of constraint given like here, then this is not an exact differential form, because the variation will not vanish due to the lingering variation of z here. But if we take this to be the time derivative of z, then this is indeed an exact differential form, and the principle outlined here makes sense when we want to consider its application to this problem. And in that case, the equations of motion are simply the ones listed here. And together with the equation of constraint, they allow you to determine the unknown functions of time x, y, z, and to find the time derivative of mu. So when the variational principle is applicable, constrained systems are equivalent to unconstrained systems subjected to generalized forces that reproduce the original constraints. This is the general result that is true both for holonomic and semi-holonomic systems. Again, with the critical point that in the case of semi-holonomic systems, we need to ensure that the equations of constraint given in a differential form are exact differentials and that they do not vary along with the variation of the system's path of motion, because in that situation that those paths are simply not geometrically possible, because they essentially they describe different dynamical systems subjected to different constraints. So in any case, when this result is valid, the forces of constraint are not eliminated, but rather they are supplied as part of the answer. And as another interesting remark, if we look at the variational condition, so the variation of the action integral needs to vanish for the correct path through the configuration space, then this can be written as the difference in two terms, namely an integral in t and an integral in u, which is the generalized potential, possibly depending on coordinates, velocities, and time for a monogenic system. And in this particular expression, we can keep the kinetic energy on the left-hand side and move the second integral on the right-hand side. And if we do that and apply the variation by the same method that was used up until this point, then we obtain the result here. And we know that up to the sign, this is simply the expression of the generalized force Q of index K. So the conclusion is that the difference in the time integral of the kinetic energy on variation is minus the time integral of the work done in virtual displacements. The work is done only by forces derived from the generalized potential. If Hamilton's principle is to hold, forces of constraint can do no work in virtual displacements delta Q of index K, be they semi-holonomic or holonomic in nature. In practice, the matter is of little handicap, as semi-holonomic problems typically involve rolling without slipping. A holonomic equation of constraint given by the functional relation here, so a constraint depending on the generalized coordinates, is equivalent to equation 224, provided that the varied paths are geometrically possible. So once again, both holonomic and the semi-holonomic constraints that we have discussed previously can be treated under the same umbrella as long as the equations of constraint themselves remain invariant when we vary the path of motion of the system in configuration space. So the variation of the path involves a vanishing variation of the equations of constraint. Then the Lagrange multiplier method is useful for holonomic systems if either reducing the generalized coordinates to an independent set is inconvenient, or if we want to find the force of constraint. As an example of the method, we can consider a hoop of radius a rolling down an inclined plane of angle alpha and length L, The coordinates are the roll distance x and the angle of rotation phi. Rolling without slipping implies the following relation. So the velocity of a point on the circumference of the hoop is equal with the velocity traveled by the, let's say, the point of contact of the hoop with the inclined plane. The moment of inertia of a uniform hoop rotating about its symmetry axis is given by the integral here. It's very similar to moments of inertia we have calculated previously. So we have a constant density rho, which is distributed on a ring of radius a about the center of mass of the hoop, and it's a very simple calculation which leads to m times a squared, where m is the mass of the hoop and a is its radius. And then the kinetic energy is simply the kinetic energy of the center of mass of the hoop, to which we add the kinetic energy for rotation about the center of mass, which is the term here. And the potential is written such that it has a maximum value at the top of the plane. So before the hoop has traveled any distance along the plane, and it is minimum when the hoop has reached the bottom of the plane. And the Lagrangian is simply t minus v plus the equation of constraint and the corresponding Lagrange multiplier. Finding the equations of motion is quite simple and straightforward. So one of them is the boxed relation here, and the second one is given here. So these are written in general terms, considering the unconstrained system, and to both of them we can connect the two of them together through the equation of constraints, since this provides the connection between the second order derivatives of both quantities. And then the results follow immediately with the linear acceleration, the angular acceleration, and the force of constraint. So the main conclusion is that the hoop rolls down with only half the acceleration it would have if slipping on a frictionless plane. However, in a more general situation, we can consider the case of a hoop of radius a and mass m rolling without slipping on top of a fixed cylinder of radius capital R under gravity. In this case, the kinetic energy is once again given by the kinetic energy of the motion of the center of mass of the hoop plus the kinetic energy of the motion about the center of mass, this is just the rotational kinetic energy we have already discussed. And as for the motion of the center of mass itself, written in unconstrained terms, it contains part of radial motion and possible angular motion. Right, so we've just written it in polar coordinates. And then the potential energy is written such that it has a maximal value at when the hoop is resting at the top of the cylinder, and it becomes minimum when it has rolled all the way to the bottom. And the two equations of constraint are first the equation for the radius of the center of mass of the hoop, which needs to be fixed at let's say the sum between the radius of the cylinder and the radius of the hoop itself. And then I've written the constraint of rolling without slipping directly in integrated form. So it's a relation between the two angles here, one of them describing the rotation of the hoop about its symmetry axis or about its center of mass, and the second angle describing its rotation along the cylinder. So the Lagrangian is then just t minus v, to which we must add the two constraints with the corresponding multipliers. And it is once again very simple and straightforward to calculate the equation of motion for the radial coordinate, which is given here, and to it we append two conditions. First, we fix the radius of the center of mass as per the constraint prescribed by the problem, and then we also set the condition for lambda to be equal to 0. So we're looking for the point where the hoop would fall from the cylinder. And the result is the equation labeled with the number 1, which is the one given here, and connects the cosine of theta to the square of the angular velocity. And to proceed further, we can just write the total energy, so the sum between kinetic and potential energies, by taking into account the two constraints here. And what this does is this allows us to write the kinetic energy just in terms of the theta coordinate and its derivative with respect to time. And since the motion takes place in a gravitational field, which is conservative, then it is obvious that the energy is conserved, and we can set its constant value to be equal to the energy when the hoop is resting at the top of the cylinder. And from these two conditions, then we immediately find the equation labeled with number 2. And then from solving equations 1 and 2 for theta, we find that cosine of theta must be equal with 1 over 2. So the angle at which the hoop falls off from the cylinder is 60 degrees, which means that due to the presence of friction, the hoop is fixed to the cylinder for a larger angle than it was the case when we had a particle sliding down on a hemisphere without exhibiting any form of friction. Another interesting application is the following. Assume that a disk of radius capital R rolls without slipping inside the stationary parabola given by the equation y equals ax squared. The questions that must be answered are: what are the equations of constraint, and what conditions allow the disk to touch the parabola at one and only one point, irrespective of its position? To begin with, we have the equation of the parabola, and we know that the velocity of a point moving on the circumference of the disk is given by the product between the radius of the disk and the angular velocity. And we can decompose this in Cartesian coordinates depending on which quadrant of the plane where the parabola is placed we put the disk. We can get at most a change in sign between these two quantities, but it's irrelevant because what we have to do here is simply square them, add them together, bring them in the equation here, take the square root, and make use of the time derivative of the equation of the parabola. And the immediate result is the one given here. So this is the equation of constraint. And now it would be a straightforward matter to integrate it. And essentially we would obtain that in the condition of a disk rolling without slipping on the parabola, the arc length traveled on the circumference of the disk will have to be equal with the arc length traveled on the parabola. But it is not a very illuminating result, so we can keep the equation of constraint written in non-integrated form and representing the constraint between the two velocities. In order to answer the second question, we can in principle choose an arbitrary point on the parabola, but it's easiest to think of the disk being located at the origin, because at that point this particular parabola, where since its minimum is at the origin, this will be the point where the parabola has the least radius of curvature. So if we assume that the disk is there and then consider just an infinitesimal displacement around that point, then the coordinates of the Cartesian coordinates of the displaced point are given by the relations here, which are simply the approximations of trigonometric functions for small angles. And we can connect these two quantities through the equation of the parabola, resulting in the equality here, which we then solve for r. And the immediate result is that if the radius of the disk is smaller than 1 divided by 2 times a, where a is the parameter of the parabola, then the disk will touch the parabola at a single point irrespective of its position. And the same result could be obtained simply from more general mathematical considerations just by considering the differential geometry and calculating the radius of curvature of the parabola. And another problem which exemplifies the use of Lagrange multipliers is the following. Consider a particle of mass m which is suspended by a massless thread of length L. It hangs without initial motion in a gravitational field of strength g. It is struck by an impulsive horizontal blow which introduces an angular velocity omega. If omega is sufficiently small, the mass moves as a simple pendulum. If omega is sufficiently large, the mass rotates about the support. Under what conditions will the thread become slack at some point in the motion? We begin by writing the kinetic energy of the particle in unconstrained form in terms of polar coordinates. And if we will consider that the z-axis is pointing down towards the ground and that is the direction of the gravitational force, then the gravitational potential is given by the expression here. And hopefully I've written it correctly. Because let's see, so this will have a minimal value when the particle is at rest, when the thread is hanging vertically, and it will be negative, and it will go to 0 when, for example, the thread is at 90 degrees with respect to the vertical. So in any case, the Lagrangian will simply be given by t minus v, and to which we must add the equation of constraint, namely that the length of the thread is fixed, and this is multiplied with the coefficient given by the unknown Lagrange multiplier. It is a straightforward matter to calculate the radial equation of motion, and if we also apply the constraint of fixed thread length for it, we will immediately obtain the result here, which gives lambda as a function of phi and its derivative with respect to time. Now, if we impose the condition that lambda equals 0, which is equivalent to saying that the tension in the thread vanishes and the thread grows slack at some point, then we obtain the boxed equation labeled with the number 1 in terms of the parameter omega 0 squared, which is just the square of the natural frequency of oscillation for the system, which is just g, the gravitational acceleration, divided by L, the length of the thread. And now for this equation to make sense, notice that cosine of phi has to be negative, so phi must be somewhere between pi over 2 and pi in order for lambda to vanish. And then if we look at the total system's energy as a function of time, this is just kinetic energy plus the potential energy, and it is a conserved quantity, and the initial energy has to be equal with the initial kinetic energy, which is given by the impulsive blow which set the system in motion, to which we must add the initial potential energy of the system being at rest. And now if we put the two together, we obtain the equation here. And then if we also bring equation 1, which connects cosine of phi and the square of phi dot, we will immediately obtain the boxed result here, which gives cosine of phi as a function of omega 0 squared and the value of omega squared, which is the initial angular velocity imparted by the impulsive blow. And now, since we know the range in which the range of values of phi in which the thread can grow slack, by plugging them in this equation and solving for omega, we reach the following conclusion, that in order for the thread to grow slack at some point in the motion, the ratio between omega squared and omega 0 squared must be located in the range between 2 and 5. So if this ratio is smaller, the system will exhibit simple oscillations around the equilibrium point. If the ratio is larger, the system will rotate about its support, and if the value is somewhere in this range, then the the particle will move up with a stiff thread up until reaching a specific point given by the angle phi, and then the thread will grow slack. A well-known problem that can be treated by the method of Lagrange undetermined multipliers is that of a particle of mass m sliding without friction on a wedge of angle alpha and mass capital M that can move without friction on a smooth horizontal surface. We are to find the equations of motion for the particle and wedge using Lagrange multipliers. We are also to find the forces of constraint. We are to calculate the work done by them in a time t, and we are to investigate any conserved quantities. We should also compare the situation with that of a fixed wedge. We will in fact begin with the case of a fixed wedge, as it is the simpler and less general one. And in the first instance, we will consider a coordinate system that is fixed at the bottom of the wedge and has the y-axis normal to the wedge's surface. As such, the force of gravity acting on the particle is decomposed as in here. And from this expression, we can construct a potential energy, which hopefully is the one I've given here. And we also need to keep in mind that for this particular choice of the coordinate system, the y-coordinate of the particle is going to be fixed at a null value. And as such, we can write the Lagrangian of the system as being the kinetic energy of the particle minus the potential energy, to which we append the equation of constraint multiplied by this unknown Lagrange coefficient. And now it is very straightforward to calculate the equations of motion. For the x-coordinate, we find that the acceleration on the x-axis is precisely the x component of the force. And in the case of the y-coordinate, by writing the terms of the equation down and using the constraint, we find that the undetermined Lagrange multiplier is in fact the y component of the force. So it will be the reaction of the wedge's surface to the presence of the particle. But notice that we have not obtained the correct sign, and this is because of the reason discussed previously, namely that since these are introduced with arbitrary signs in the Lagrangian, we can only calculate their magnitudes correctly, and the sign must be determined from understanding the physics of the problem. So yeah, so the force acting on the particle is acting down, but no, this is in fact correct. So yeah, this is correct because the reaction force of the wedge will be pointed in an opposite direction from the force of gravity acting on the particle. Now, as another example of this case, we can instead opt for a frame normal to the surface upon which the wedge is fixed, and then the constraint is a bit more complicated, and essentially I'm just writing the tangent of the wedge's angle in terms of the y and x coordinates. And in this case, the Lagrangian will once again be the kinetic energy of the particle minus its potential energy written in this new coordinate system, and to which we add the new equation of constraint multiplied by the Lagrange coefficient here. And now if we calculate the equations of motion, we find the two boxed results, the one here and the one here. And then we can use the constraint equation itself, so the result here, to find a connection between the two accelerations. And having this, we can solve the system and find the results listed here. So once again, the force of constraint acting on the particle and the two equations of motion for the x and y coordinates. We can consider now a coordinate system normal to the surface and the wedge being free to slide as a reaction to the particle moving. So now the situation is a bit more complex, and the kinetic energy has two terms, one belonging to the motion of the particle and one to the motion of the wedge. The potential energy will as well have two terms, a potential term for the particle and a potential term for the wedge, and we will have two constraints. The first constraint is, just as in the previous case, involves the fixed angle alpha, but the tangent is written in terms of the coordinates of the particle and wedge for the y and x directions. And we have a second constraint, which is quite a lot simpler and simply says that the y coordinate of the wedge is constant and equal to 0. So the wedge is not allowed to move up and down. In this coordinate system, at least, it can only move left and right as it slides on the surface under the action of the particle. And then we can write the equations of motion for all of the involved coordinates. So the first result is the equation of motion for the x coordinate of the particle, then the y coordinate of the particle, and the x coordinate of the wedge. And if we want to write the equation of motion for the y coordinate of the wedge, which is the result here, but also apply the constraint, then we find a relation which connects the two undetermined Lagrange multipliers in terms of known quantities, which should be the mass of the wedge, the gravitational acceleration, and the angle of the wedge. And if we take the time derivative of the constraint acting on the particle, so of the constraint here, then we can find a connection between these free accelerations. And now it's very straightforward using the boxed results to obtain the following list of conclusions. So the values of the two undetermined Lagrange multipliers and the accelerations of the particle and wedge. And to test the consistency of these results, we can play with them. For example, in the first result, if we set the mass of the wedge to infinite, so essentially this would be an immobile wedge, we obtain the previous result from the case of a stationary wedge. And in the second equation, if, for example, we set the mass of the particle to be equal to 0, then the force of constraint on the wedge is just the reaction of the surface to it, so it's just the weight of the wedge in magnitude. And for example, here, if we set the angle alpha to be equal to 90 degrees, then this and this simplify, and what is left is just the weight of the particles as it falls under gravity. Furthermore, from all of these results, it is very easy to verify that the following relation holds. So this quantity is constant, and this is simply uh, the x component of the linear momentum for the center of mass of the system. So essentially what we are seeing is that this quantity is conserved because there is no external force applied on the system in the x direction. The action and reaction between the particle and wedge will cancel each other out in the x direction and produce no net force. And in the case of a fixed wedge, we can calculate the work done by the force of constraint in a time t as follows. So we know that this is the force of constraint. We can write its components in the x and y direction. So hopefully I've done this correctly. And we know from the equations of motion, we know the laws of motion for the two coordinates. And then it's very simple to apply the basic definition of work and to calculate its value over a time t as being the line integral for each component of the force along the given direction for a range of coordinates corresponding to the time t. And in fact, what follows by adding these two together is that the total work of the particle in the case of a fixed wedge is the total work done on the particle by the force of constraint is 0. And very similarly, you can check in the case of the moving wedge that the total work done on the particle plus the work done on the wedge by the forces of constraint is indeed equal to 0. In summary, and as an outlook for what is about to follow, we have generalized Hamilton's principle to systems subjected to holonomic and semiholonomic constraints. We have derived the respective Lagrange's equations for the generalized principle by introducing Lagrange undetermined multipliers, which act as the forces of constraint. We have discussed applications involving both static and dynamic constraints for which Hamilton's principle is applicable in the generalized form. And in the following, we will discuss the advantages of variational formulations of classical mechanics. I want to thank you very much for watching the video. I hope you found it worth your time, and I will catch you later. Goodbye.